Hello, so in this video we're going to look at a type of logarithm called the natural logarithm. So last time we looked at solving equations like 2 to the x equals 3, and then we could solve for the power x. And so what we said was we can take logs of both sides. In the same way, we can add both sides or subtract both sides or multiply by both sides. We could take logs of both sides of the equation. And so we saw that log of 2 to the x is log 3, right? And we also discussed that this log, the log, if I don't specify base, because obviously every log has a base, right? And then my number. But if there's no base, then we say that's log 10. So log is just log 10. Okay, that's a common log, which you need, and that's just how we represent log 10. We're lazy, so if we reference log 10, we just say log. And so then if we proceed to solve it, we could just move the power x in front. So then x log 2 is equal to log 3. And therefore x is log 3 divided by log 2. And that would be 1.58 to 2 decimal places, right? So we still have to do that by taking logs. What we're going to look at now is actually another particular type of log. So we saw log 10, right? We used that. That's one common log. Another one is log base e. Okay. Now again, remember e is just a number. We looked at that before. E was like 2.718 ... right? E is a number, but in particular e was very special. We saw it earlier on in the chapter. We use e quite often with exponential modelling and stuff to do with derivatives and stuff like that. So it's again a very common log, okay? And it's so common that actually, like with log 10, we've got sort of special notation for it. Log e, log specifically the base e, is called ln. Okay, ln. This is pronounced lun. Okay, lun. There we are, lun. And it's on your calculator. It's next to the log button. So you've got a log button and a lun button, an ln button next to it. So actually ln is just a log with base e. Okay, it's the natural logarithm. Okay, this is a natural logarithm. And actually, because it's condensed, right? It's quite short. It's easy to use. We can use this is the most common base, the common log to solve equations, right? When we take logs, we're going to be using ln, okay? And we're going to be working with that in this section. Yeah. So it's quite a useful logarithm to know. And actually what we also need to do is to be able to sketch ln. So what is ln? Ln of x, right? And again, alternatively, that's log e to the x. Okay, so we need to be able to sketch a log graph as well, particularly ln x. Okay, so how are we going to do that? Well, recall that e to the x looks like this, right? And it passes through 1. That's y is e to the x. Now, why e to the x? Because actually, remember, exponentials and logs are inverses. They're inverse functions. And so then, in particular, e to the x is inverse of ln x, because e to the x is the inverse of log base e. Okay? Now, to sketch inverse graphs, we will look at this in year 2, but with inverse functions. So if I draw a rough line here, this is y is x, y is equal to x. If I make it a bit straighter. Okay, it's a bit curved, but it's y is equal to x, right? That's meant to be a straight line. This is the line y is equal to x. Now with inverse functions, you'll see in year 2 that inverse functions are reflections in this particular line, y is x, because the idea is with inverse functions, the x and the y kind of swap roles. Okay, so that means when I'm reflecting in this line, I'm switching y and x to invert it, right? And I've just redrew that line, y is equal to x now to be more straight. Okay, so if I reflect the y is equal to x curve across the line, then this line y is x, that if I pick some points, then let's say this point here firstly, if we were to reflect it in the line, then we go perpendicular and it would end up somewhere here, let's say, right? Then let's take this point here, that would move somewhere there. And then if we take this point, the y-intercept at 1, what would happen is it would move on the x-axis at 1, okay? Now it would be on the x-axis, not on the y-axis. Then if we take, let's say, this point here, well, it would just be there, roughly. And then if you take this point here, that would be there, somewhere there. And so actually, if we consider the red points now over the line, these red points are mapped. I can start to draw a curve connecting the red points. So if I draw the curve, it would look something a bit like this. Something roughly like that, right? And then if I continue the y-axis down, then actually you can spot that this red curve is going to be my ln graph. This is going to be y's ln x. Okay, which is a reflection of the e to the x curve. So it's the inverse function. So if I was to just draw ln x then, with this red curve here, well, the key feature is it passes through 1. And actually notice, if we were to continue the red curve on, if we were to continue it down, it would tend towards negative infinity down the y-axis. Like how on the e to the x curve, it tends towards the x-axis. Now it's tending towards the y-axis down, okay? So the ln graph is going to look something like this, okay? Y is ln x. And that is the graph you need to know. You need to know this graph of ln x. You don't need to know any other log graphs. You don't need to know what log 2 looks like or log 10 looks like. But all log graphs will look pretty similar, okay? If you're ever in a position where you need to sketch a different log that isn't log e or ln x, it will look pretty damn similar. It'll be pretty similar. It will still pass through 1. All log graphs will. But this, in particular, ln x, you need to be familiar and be able to draw this graph, okay? You need to remember this graph here. And the fact that also there's an asymptote, right? We can see asymptote on the y-axis, which is x equal to 0, okay? You need to know this, right? But that's how we get the graph. Again, we'll look more about that in year 2, about how we can draw inverse functions in this way. But yes, you do circle it. You need to remember the ln x graph, okay? Okay, one final thing to note actually with the graph is the graph looks like it's just leveling off. Like, it looks like it's going towards some sort of asymptote, right? That's not what happens. Essentially what's happening is it is going up and up and up and up and up. You can see that, right? If I continue the line, it is going up, but towards infinity, but it's going up extremely slowly. Log graphs are known for being very slow in growth. So growing towards infinity, it's very slow, but it does happen. Do not be fooled. It's not going towards an asymptote and leveling off at 0. It's still going up. Well, not like that, but as you just see, it will still go up, but extremely slowly, okay? So do not think that it's just leveling off to 0, right? It's still going towards infinity. Okay, so that's the ln graph. One more thing we need to know. Well, first, a key thing result that might help is that ln e is simply 1. Okay, because what that's saying is, remember ln e, remember is log e to the e is equal to 1. Okay, that makes sense because remember with logs, what we're saying as a log is the base is e, the base e to the power of 1. That's why power 1 equals e. That makes sense, right? E equals e when the power's 1. Okay, so ln e is 1. Okay, you can put that in your calculator, press the ln button and then press in e, and then you will get 1. Okay, but ln e is 1 for that reason. And another thing you need to know before we move to questions is, and this will help with solving equations later on, is the result that e to the ln x is always x. Okay, always x. That is because if we let's say e to the ln x then equals y. Obviously, I'm not telling you it's x at the moment. Let's just say it's equal to y, right? Y is e to the ln x. If we take logs of both sides, and particularly I'm going to take logs of ln y is now ln e to the ln x. Okay, and actually then I can use my log law, where the power ln x can move to the front, so then ln y is ln x times ln e, right? Now ln e we just discussed is 1, so therefore ln y is simply ln x, right? Ln x times 1, but that's just ln x. Therefore, if we just compare what's in the log, y is equal to x. Well, there we are. So then if y is equal to e to the ln x, therefore x is equal to e to the ln x. So what that's saying is essentially if we raise a ln x to the power e, that just results in x, what we got inside the log. You can think of this again, because exponentials and logs are inverses. I've got an exponential e that cancels with the log e, so the inverse functions, they cancel out to just leave me with x. Either way you can think of it, but you do need to remember this. And actually in general the same is true, that for any base that isn't just e, a to the ln x, no, a to the log a of x, sorry, is always equal to x as well. So any base that's raised to the log of that base will always just get me what's inside, so x. Okay, we can cancel it down. Okay, the base will cancel the log of that base to just leave me with x. But this is the most common one. Okay, e, because we use e a lot, e to the ln x is just x. Okay, and you need to remember that. Okay, and in the formula book you are given you are told that formula, actually it's here but it's written in a different way. E to the x ln a is a to the x. Okay, so how can we use this formula? Well, what we can do here, we can simplify the exponent, so x can come as a power, so then we can say e to the ln a to the x is a to the x. Well, there we are then. If I just call a to the x y, or some other number, then e to the ln y is just y, which is the exact same thing. Okay, just different letters. But there we are. But honestly, I wouldn't revise the way the formula book says it. It's a bit awkward. I'd revise the formula I've just stated, right? E to the ln x is x. But there we are. So in essence, you need to remember the ln graph and this little identity, this little formula here, this there. Okay, and just a little side note, this other formula you'll see in the formula book, we don't use it. This is called the base change formula. We don't use it really on this course, and that is basically saying that log base a of x is log base b of x over log base b of a. So it's in the name, right? Base change. If we want to switch the base of one log to another from a to b, this is how we can do it, okay? If you might find it handy, some question maybe, but you won't be expected to use it or even know it really. It's just there, I guess, to help. I don't know if someone finds it useful. But if you see that formula in the formula book, don't freak out. It's just there to help, but it's not really in the course. So yeah. Okay. So let's have a look at some questions then. Right. So we need to solve these equations. So firstly, we have e to the x is 5. Now, like with last time, we're going to take logs. I'm going to take ln. Okay, so ln e to the x is equal to ln 5. So then x ln e is equal to ln 5. If I bring the power to the front, well, actually ln e is 1. So therefore x is just ln 5. There we are. Cool. Part B, it wants to pay attention. It wants you to answer an exact form. That means no decimals. Ln or log is exact form. Okay, just like with fractions or anything like that. Part B, we have ln x is 3. Want to solve for x. What we can do here is, again, you could recognise that this is log base e of x and then convert it straight into exponential form. So then e to the power 3 is equal to x. So x is e to e cubed. However, what we can do instead is raise and take exponentials and raise both sides by a power, particularly power to the e. So e to the ln x is e to the 3. Now remember my formula. My formula just explained that e to the ln x is just x. So that means x then equals e cubed, and I can get x that way, right? Okay, there we are. Okay, I now need to solve these equations. So I have e to the 2x add 3 is equal to 7. So again, if I take logs, ln of e to the 2x add 3 is ln 7. So then I can bring the power here to the front. So then 2x add 3, lots of ln e is ln 7. But what do you know? Ln e just goes to 1. So then 2x add 3 is equal to ln 7. Then I can just rearrange for x. So then 2x is ln 7, take away 3. So then x is ln 7, take away 3 over 2. And there we are. Cool. So that's the answer in exact form there, okay? Not a nice form, but it's still exact. The precise answer for x. Part B, we have 2 ln x add 1 is equal to 5. Right, so first thing I'm just going to rearrange to get ln x on its own. So then 2 ln x is, if I take away 1, I get 4. So then ln x is 2, if I divide by 2. Now at that point, again, you can solve this many ways. Again, probably the best way is to raise by a power, so e, because obviously we're dealing with ln, which is e. So e to the ln x is e to the 2. Well, again, e to the ln x just goes to x. You can think of that as the e cancelling out with the ln. So then x is e squared. And there we are. Part C, we have e to the 2x add 5e to the x is 14. Right, now this one's quite interesting. This is another disguised or hidden quadratic, which we looked at in quadratics, also last time actually as well. We looked at tackling hidden quadratics with exponentials. Here we've got e, and we could do the same thing here. If I move the 14 to the other side, so e to the 2x add 5e to the x is minus 14 equals 0. This is a quadratic equation. Well, how can we notice that? Well, actually, if I said e to the 2x is e to the x squared, remember I can split up the power in this way. Add 5e to the x minus 14 equals 0. Now, hopefully it's very clear. If I now say that u is e to the x, well, what do you know? Then u squared, e to the x squared, u squared, add 5u minus 14 equals 0. There we are. Cool. So now if I does it factorize? So minus 14 and add to get 5. The factors 14 and 1, 7 and 2. Yes. And in particular, I'm going to want to take 7 and minus 2 as my factor pair, because then 7 times minus 2 is minus 14. Add them to get 5. So that factorizes to u add 7. U minus 2 equals 0. So then u is minus 7, or u is 2. But of course, I'm solving for x, not u. Remember, u is e to the x, so that means e to the x is minus 7, or e to the x is 2. Now, with this first one, hopefully you can spot that is not valid, because e to the x is, or any exponential is always positive. Remember, the e to the x graph looks like this. That's always positive. It's above the x-axis. It's on the positive y-axis, so it's positive. So that cannot happen. E to the x cannot be negative. Therefore, no solutions here. Okay, but what about this? E to the x is equal to 2. Yes, we can solve that, because if we take logs, ln of e to the x is ln 2, then x ln e is ln 2, where again, ln e just goes to 1. So then x is just simply ln 2. That's my answer. By the way, here, if you didn't spot that it couldn't be negative, if we were to proceed to solve in the normal way, you'd still spot that, because if we took logs here, so then ln e to the x is ln minus 7, but hopefully you do spot here that you can't have a negative in the log, so that will be undefined, so no solutions. And if you were to put that in your calculator, you'd get math error. That would be why. So there we are. So that's the only solution here. X is ln 2. Cool. Right, so again, we've got some exercise questions, and we need to solve this hidden quadratic e to the x add 12 e to the minus x equals 7. So first thing, I'm going to just move the 7 to the other side. Now, it's not very clear that this is the hidden quadratic. I've not got e to the 2x, I've not got something squared at the moment. It's quite weird. I've got e to the x and e to the minus x. This is a hidden quadratic, and it's honestly this is a fairly common one, so it looks weird at the moment, but hopefully you do understand the process here, and then you can be able to tackle questions like this. To help you visualize, well, actually, if I notice e to the negative x is reciprocal, right? It's a negative power. I can say that e to the x at 12 over e to the x minus 7 equals 0. Now, to get rid of the fraction, I can times by e to the x to all sides, right? So then e to the x times e to the x. Well, what's that going to be? If I'm multiplying in this way, I can add the powers, right? Well, what's x add x then? That's 2x, right? So e to the 2x add 12, take away 7e to the x is 0. Hopefully with me there. Now, if I rearrange ever so slightly, e to the 2x minus 7e to the x add 12 equals 0. Hopefully now you spot that's pretty much identical to the last equation we saw. Now I could split this up as e to the x squared, take away 7e to the x add 12 equals 0. Okay, now you can hopefully spot we got a quadratic. If I say u is e to the x, then u squared minus 7u add 12 equals 0. Does that factorize? 12, add to get minus 7. 12 and 1, 6 and 2, 4 and 3. There we are. So that's my factor pair. I'm going to want to make both of them negative, because then they're multiplied to get positive 12, add to get minus 7. So u minus 4, u minus 3 equals 0. So u equals 4, or u equals 3. But of course I want to solve for x, so u is e to the x, so then e to the x is 4, or e to the x is 3. And both have solutions. So then if I take logs here, then ln e to the x is ln 4. And so x ln e is ln 4. Well, ln e is 1, so therefore x is ln 4. And you can probably spot the next one's going to be ln 3, but let's go through it. So then ln e to the x is ln 3. So again, x ln e is ln 3. So x is ln 3. Because ln e goes to 0. Those are my two solutions. Cool. There we are. So again, hopefully you're familiar with that. Sometimes they do like asking this type of hidden quadratic, this particular one, where you got e to the x and e to the negative x. Hopefully spotted how we can transform that into a quadratic, like we did here. Okay. Right. Okay, now we need to solve this trickier question. So we need to solve 3 to the x e to the 4x minus 1 equals 5 in this form here. Okay, so let's not worry about that just yet. It looks a bit ugly, but let's not worry about it. Let's just solve in the normal way. Well, if we just take logs firstly, ln to the 3x e to the 4x minus 1 is ln 5. Now, what we're going to do here? Well, actually, there are many ways of tackling this. You can kind of like make the indices nicer and kind of factorize in some way the powers, but I think the easiest way is actually noticing it. I've got a product here. I've got 3 to the x times e to the 4x minus 1. Remember my log laws, I could split up a product into two different logs by adding them. So ln 3 to the x add ln e to the 4x minus 1 is ln 5. Now hopefully it's a bit more apparent what we can do. So we can bring the power to the front. So then x ln 3 add 4x minus 1 ln e equals ln 5. Well, again, ln e goes to 1. So x ln 3 add 4x minus 1 equals ln 5. Now to solve for x, I just need to factorize x. So let's keep the x's on this side. So I'm going to have x ln 3 add 4x. If I add 1, I get ln 5 add 1. And then I can factor an x out. So x of ln 3 add 4 equals ln 5 add 1. And then simply x then is going to be 1 add ln 5 over 4 add ln 3. And that is my answer there. And hopefully you recognise it's in that form now. Okay, cool. So hopefully you're starting to become quite confident how you can solve these various equations by taking logs and taking lns. But there we are. Okay, we've got this question here. It's to do with the ln graph, which again you do need to remember. But they've given this particular one here. So y is 3 add ln 4 minus x. We need to find the coordinates of a firstly. Well, what do you notice about a? It's on the y-axis, the y-intercept. So that is where x is 0, right? So if I set x is 0 into y, the curve y is 3 add ln of 4 minus x. Well, then that'd be y is 3 add ln 4, right? 4 take away 0 is just 4. And that's the exact coordinate then. So that's the y-intercept. So that means the coordinate a is xy, but x is 0, y is 3 add ln 4. And so for part B now, well, we need to find the coordinates of point B there. Where again, B is now on the x-axis, so that's when y is equal to 0. So if we set y 0 to my curve here, 3 and ln 4 minus x, that means that 3 add ln of 4 minus x indeed equals 0. So then ln of 4 minus x equals minus 3. Don't panic here. Logs can output a negative number, right? Think about the log graph. Here, you know, logs can be negative, okay? So don't be thrown off by that. That still has solutions. So we can proceed, and we're going to take exponentials to both sides. So e in particular, e to the ln 4 minus x is e to the minus 3. And then obviously the e and the ln cancel out, so then 4 minus x is simply e to the minus 3. So then minus x, if we subtract 4, that's e to the minus 3 minus 4. And then just to get x then, divide by minus 1, x is 4. Or minus e to the minus 3, add 4. or x is 4 minus e to the minus 3. And that is my answer. So then the coordinate b then, so b, x is 4 minus e to the minus 3, y is 0, right? And that's my coordinate for b. Okay, so we're going to look at modelling questions now. And so actually, now that we've got the theory of the logs and how we can solve equations and stuff using logs, we can actually solve more detailed exponential modelling questions now. So here, we're told in 1960 the population of Mozambique is 7.6 million, and in 1980 the population is 12.1 million. The researcher wants to model the population in p million people, p million, as a function of t, where t's time in years since 1960, right? Okay, so let's talk about population over time. So firstly, it asks to find a linear model between p and t. So a linear model, you need to know its y is mx plus c, right? So it's a straight line. Well, here we don't have y and x, we have p and t. So p is equal to mt add c. Okay, now we need to find m and c, the gradient and the y-intercept, or the p-intercept technically. But I've got these two conditions here, right? These two conditions. 1960, the population is 7.6 million. Well, time, t is years after 1960. So at 1960, that's the initial time. That's when t is 0, right? That's the start. So t is 0, then the population, well, 7.6 million, but it wouldn't be 7,600,000 million, right? It'd be 7.6, because remember, p is in millions, right? So 7.6 million is just 7.6 there. Okay, so that's my first condition. So t is 0, p is 7.6. So I could sub that in. So then p 7.6 equals m, lots of 0, add c. Well, that's just 0, so therefore c is 7.6. So p is mt at 7.6. Now, I'm also given this in 1980. It was 12.1 million. Well, okay, 1980. Well, what value of t is that? Well, t starts at 1960. T is 0 at 1960. So how many years have we gone from 60 to 80? 20 years. So that would be 20 more. That would be t's 20, right? So t's 20. That would mean that then p, well, it's 12.1, right? Million. But there we are. So if I then sub that in, so t's 20. P is 12.1. Yes, that means that therefore P is 12.1 is going to equal mt. So m lots of 20 add 7.6. So then 12.1. If I take away 7.6, right? 12.1 take away 7.6. I get 4.5. 4.5 is 20m. So therefore m is 4.5 divided by 20, which is 0.225. Therefore my final equation is p is 0.225t, add 7.6. There we are. That's my linear model. So again, a linear model, we looked at that in straight lines in chapter 5. What we mean by linear model is essentially y is mx plus c, like a straight line, right? Now, then for part B, it says use an exponential model of the form p is ab to the t. So p is ab to the t. So it's an exponential equation, and we need to find. We basically need to find the values of a and b. Okay, essentially. So again, I've got these two results here, right? T0, P is 7.6. So T0, P is 7.6. So what we can do here now is that now that we know logs, we can basically derive and work out different exponential models, different equations now, right? And it's quite a common exam question to find like missing values in this equation, A and B, right? So I can use my data here, my this result, to substitute into the equation. So 7.6 for P is going to be AB by T0, right? Well, B to the 0, we remember that anything to the 0 pretty much is 1. So that means 7.6 is simply A lots of 1, which is just A, right? There we are. So then P is now 7.6 B to the T. Now I just need to find B. But remember, I'm also given this here. When T is 20, P is 12.1. So if I sub that in, that means 12.1 for P is 7.6 B to the 20. Okay, now I need to find B. This is where logs are going to kick in. Well, firstly, I can say that B to the 20, if I divide by 7.6, 12.1 divided by 7.6. And it's not very nice. I'm just going to leave it as 12.1 over 7.6. Oh, no, actually, that'd be 121 over 76. There we are. Now, that's B to the 20. So then B is going to be the 20th root of 121 over 76. Now, this would actually also be plus or minus. You need to remember with positive square roots, so 2, 4, 6, 8, 10, right? And an even root has plus or minus. If it's an odd root, like cube root, then it's just one value, but with even roots it's plus or minus. So that means B would be plus or minus. If we work out the 20th root of this, of 121 over 76, we get plus or minus 1.0235. Okay, so we've got two values. Okay, but let's think about it though. If B was B can't be negative actually, can it? No. Because with exponentials can only have a positive. So A to the X, right? Any exponential A to the X. As we discussed, A must always be positive. So actually B must be positive. So therefore B is just simply positive 1.0235 to 4 decimal places. Okay, that also makes sense because if you think about it logically, if B was negative, the model will basically, well, when it does work, because it wouldn't work all the time, but if it did work, it basically saying you're getting negative population, which makes no sense. So there we are, B is positive in this case. So that means my final equation is P is A, which was 7.6. B, now B is 1.0235 to the T. And there's my equation. Cool. Okay, then it says in 2010, the population was 23.4. So as physical numbers then, T and P, what does this convert to mathematically? Well, 2010, what value of T would that be? So initially, when T is 0, it's 1960. How many years have we gone from 1960 to 2010? 50 years, right? So T would be 50, and then P would be 23.4. Okay, then it says, explain which of my two models is best supported. So basically it's saying, which model is the closest to this answer? Okay, so T is 50. T is 50, P was 23.5, was it? I can't remember. 23.4. I was close. So what we're going to do, it says, with this in mind, which model is best supported by this fact, by this result here. So firstly, what I'm going to do is I'm just going to literally plug in this answer, this result, into each equation, into each model, right? Well, firstly, we've got P is 0.225. So first, P is 0.225t, add 7.6. So then I'm going to sub in t is 50. So t is 50, P is 0.225 of 50, add 7.6, which would get me 18.85, right? It's not, I mean, I guess it's not miles away, but it's not ideal, really. 23 to 18, it's not the closest, but let's have a look. Now, secondly, we're going to sub it into the exponential model, which we just worked out, right? Here, P is 7.6 lots of 1.0235 to the t. So then again, when t is 50, P is going to be 7.6 lots of 1.0235 lots of 50. And so that would be 24.277. Okay. Well, actually, which answer then from this, from the straight line, and from this, the exponential, which one is closest to 23.4, the true value of P? Hopefully, it's going to be the exponential one. So the exponential model is more reliable. What does it say exactly? Which is best supported? Okay. It is more reliable, I'd say. More reliable because it gives a closer approximation. Because at the end of the day, these models are just approximations of the data, right? Of this scenario. Gives a closer approximation to P is equal to 23.4 when t is 50. Okay. I guess you could add a comparison and say that 24.3 is closer to 18.9, right? So the exponential result compared to the linear result is closer to 23.4. And there we are. Okay. So hopefully it made sense. But yeah, so again, we can deal with exponential models like this with exponential equations by taking logs, okay, to solve them, find certain information out. Okay, so we've got some exam questions on this. So here, I'm told that the temperature of a cup in T minutes, underline the units, and the temperature is in degrees. Okay, I'll leave it there. The temperature is modelled by theta. The temperature theta is 18 add 65 e to the negative t over 8. Now it says find according to the model the temperature when it's placed on the table. So hopefully you recognise that's talking about the initial time when t is 0 at the start. Because remember, the temperature is t minutes after it was placed on the table. When it was placed on the table, that's at the start, right? So simply t is 0, then theta is going to be 18, that's 65, lots of 0 effectively, right? T over 8, 0, if t is 0. Well, 65, oh no, e to the 0, sorry. Well, anything to the 0 is practically 1, so that's 18, add 65, lots of 1, which is 18 add 65, which is 83. 83 degrees Celsius. And there we are. Part B then, it says find the value of T when the temperature was 35. So now that's the temperature theta is 35. So if I sub that into here, the equation then we get is 35 equals 18 as 65 e to the negative t over 8. And so if I subtract 18, firstly, 35 take away 18 is 17. That would equal 65 e to the negative t over 8. If I divide by 65 then, I get 17 over 65 is equal to e to the negative t over 8. And then if I take logs to both sides, if I take luns of both sides, I get ln of 17 over 65 is equal to ln e to the negative t over 8. And again, then I can bring the power of e to the front. So ln 17 over 65 is minus t over 8 lots of ln e. Well, again, ln e goes to 1, right? So that means simply minus t over 8 is ln 17 over 65. Right, so then I can times by minus 8 to both sides to get rid of the fraction to get t. So simply t is minus 8 ln 17 over 65, right? Now that's t. If I put that in the calculator, that would be 10.7 minutes, right, mins to one decimal place. Yes, to one decimal place. There we are. There we are. Cool. Right. Then it says for part C, explain why, according to the model, the temperature of the cup could not fall to 15 degrees C. Right. So this is basically saying, he's talking about the long term, right? Long term. Because if you think about it, obviously it's talking about if you put the cup of tea on the table, over time the tea is going to cool down, right? So over time, in the long term, the temperature cannot just drop below 15. That's then meaning, remember long term, we looked at this with exponential modelling, we're talking about t going to infinity, right? So when t goes to infinity, or when t gets very large, then this equation theta equals 18, add 65 e to the minus t over 8. Well, we discussed this before as well, that the e to the negative t over 8, or e to the negative anything, e to the negative x, any x, if x goes to infinity, that goes to 0. E to the negative of anything goes to 0 when it goes to infinity, which means that this equals 18 at 65, lots of 0 basically. This e to the negative t over 8 will go to 0, okay? Which means I'm left with 18. That is what that's what the temperature theta will head towards. It will drop to 18, and that will be it, okay? And I'd say I make a reference to as e to the negative t over 8 tends to 0, okay? Remember, we did look at that before. This is a limiting value. Any negative exponential like this, e to the negative t over 8, could be anything, e to the negative any t. As long as t goes to infinity, then the whole exponential goes to 0, okay? We did look at this. Make sure you're familiar and comfortable with that idea. But the long-term value is 18 when t goes to infinity, which means, therefore, the temperature theta does not drop below 18 degrees Celsius according to the model. So therefore does not reach 15 degrees, because the question talked about if it went to 15 degrees, right? Not 18 but 15 degrees, and that's my answer there. Okay, we're going to build on that more. The next part of the question is going to talk about this t goes to infinity as well. So we're going to look at this again here. So we're given this graph here, and this graph is a different temperature of mu, right? This little funny shape here, mu, that's a Greek letter, that is mu. If you've not seen it before, that's how we say it, that's why how we write it. It's just another letter, it's another variable, right? Mu, this little funny U shape of a second cup, so a different equation, is mu is now A, mu is A, add B e to the negative 2 over 8, okay? And you guessed it, we're probably going to need to find A and B, right? The missing letters A and B. And it's talking about how we got 2 data points, 2 coordinates here, right? And we're also given an asymptote with the line L, okay? It says to find an equation for the asymptote, but we got given these 2 points as well. So what we can do is substitute these 2 points in to find A and B here, right? So firstly, 0, 94, right? The y-intercept. So 0, 94. What does that correspond to? That means when t, right? T is sort of the x variable, so t is 0, and mu would be 94, right? So if I substitute that in, that therefore means that 94 for mu is going to be A at BE to the 0 effectively, right? E to the 0. Or again, E to the 0 is just 1. So we get 94. A at B is equal to 94, right? I'm also given the coordinate here of 850. Now again, that means t is 8 and mu is 50. So therefore, again, that means that 50 for mu is going to be A at BE to the negative 8 over 8. Well, that's just minus 1 then, right? Minus 1. Okay. Right. Not much we can do here, but actually recognise at this point I've got simultaneous equations, right? These two here. A at B is 94. A at BE to the negative 1 is equal to 50, right? So how can I solve this? Well, actually, what I can do, I can do that many ways. I can substitute, but I'm going to use elimination. I can immediately eliminate A if I subtract both equations, right? If I subtract both equations, I'd get B take away BE to the minus 1 is 94 take away 50. Where 94 take away 50 is 44, right? And at that point, then I can factorise a B. So then B of 1 minus e to the minus 1 is 44. Therefore, B is 44 over 1 minus e to the minus 1. Okay. Right. No, it doesn't say anything about rounding it. I don't know, we have to stick with it, I guess. That's the value of B. Quite ugly fraction, but we'll deal with it. Now A. So that's B. So then I need to substitute that back into A. Well, I'm going to substitute that into the first equation, right? That's probably the nicer one. So I'm going to sub B back into the first one. So then A add 44 over 1 minus e to the minus 1 is 94. So A therefore is 94. Take away 44 over 1 minus e to the minus 1. Okay, that's quite horrific. Right. So what I'll tell you what, I'll give it as a decimal then. So 44 over 1 minus e to the minus 1 is 69.6 to 1 dp. And A is 94, take away that. which is 24.4 to 1 dp. So my model is going to look like this. So then my model is mu. Remember, mu was a add be to the minus t over 8. So a is this 24.4 add b 69.6 e to the negative 2 over 8. Now hopefully that helps you visualize now. Okay, I'm not going to if I just put the decimals now, it's a lot clearer what we're working with. Now I've got my equation. Now the asymptote, again, the asymptote of my curve, the equation I've worked out, mu, it's the long-term behaviour, right? It's the long-term, it's what it's tending towards when t goes to infinity, right? So again, let's consider t going to infinity. So as t goes to infinity, then what does mu go to? Mu is going to be 24 add 4 at 69.6, but this e to the negative t, when t goes to infinity, that negative exponential, that goes to 0, right? So I'm left with 24.4, which is actually equal to a, okay? So the asymptote then, if we go back, it wants to find the equation of the asymptote, right? Now, we saw that the value in the long term was 24.4, right? That's the equation of the asymptote then. The asymptote is also where the curve tends to, right, in the long term, when t goes to infinity, right? So that means not y, but mu would equal 24.4 for my equation there. Okay, hopefully that made sense. That's the idea of the asymptote in the long term, what the curve tends to. Well, in this case, we saw it's 24.4. So that's the long term. So the asymptote is mu equal to 24.4 to 1 decimal place. And actually, they'd be fine with that in this case because it's quite nasty. The fraction, the leaning of that in this case. Or I could just call it a. And remember, a was this exact fraction here, but there we are. That's the asymptote. It's quite tricky, that was, especially that last part of the question there. But again, the idea was essentially I just found the missing values a and b by substituting these 2 points in, and then I can find the long-term value because the exponential goes to 0, right? The e part here, the e part goes to 0, so I'm just left with a effectively, which is my asymptote. Right, okay, I've got one more exam question here, and especially the final part is a bit gnarlier than it seems, but let's get to it. So we're told a scientist is studying the number of bees and wasps on an island. The bees, measured in thousands, always measure your units, it might catch you off guard. So thousands, NB, is modeled by the equation where T is the number of years, so years, okay? So NB, the number of bees, is 45 add 220e to the positive 0.05t. So firstly, we need to find the number of bees at the start of the study. So hopefully you recognise that means T0, right? The initial time. So T0 pi, then NB is going to be 45 add 220 e to the 0 effectively, right? But e to the 0 is 1, so that's for 45 add 220, and that would be 265. But that NB is 265, but that's not, it didn't ask for the value of NB, it asked for the number of bees, which is a bit different because NB is thousands, right? So I need to multiply by 1,000, so number of bees is 265 times 1,000. That's 265,000 bees. Right, that's why I say underline your units with these questions, because it could catch you off guard. You need to recognise the times by 1,000 there at the end. Right, part B. then says we show that exactly 10 years at the start of the study, the number of bees was increasing at a rate of approximately 18,000 per year. Now, why is rate in bold here? They're quite generous. They underlined it in bold because it is important. But what does that mean? Hopefully you recognise it means derivative, right? Derivative is all to do with rates and rates of change. So we need to compute the derivative of NB is 45 at 220 e to the 0.05t. Now we do know how to differentiate exponentials. We did that at the start of the chapter, right? Differentiating e. So in this case we need to differentiate them. So the derivative of NB with respect to t, so if we differentiate then to get the rate, so this is rate, right? Then 45, firstly, that's a number that goes to 0. So then we're left with differentiating 220 e to the 0.05t. So remember, differentiating the coefficient, the number in front of t, comes to the front. So we're left with 0.05 lots of 220 e to the 0.05t. And so that is, if we multiply that, 220 times 0.05, 11 e to the 0.05t. So that's my rate, okay? I'll emphasize it again. Rate, if you see anything to do with rate or anything like that, it always means derivative. You need to differentiate. Always differentiate when you see anything to do with rate. Okay, then it says exactly 10 years. So that means when t is 10, right? So I'm going to substitute that into the derivative. So at t is 10, the derivative dnb over dt, I'm going to plug that in t into here. So it's going to be 11e to the 0.05 of 11. 10, sorry. And so if I work that out, that would be 18.1, right? 0.1 to 1 decimal place. But let's have a look at the question. We're nearly there, but we want the rate to be 18,000 per year. Well, remember, it's talking about the bees, so we need to times by 1,000 again. So rate is 18.1 times 1,000, which is 18.1, which is then approximate to 18,100, which is approximate to 18,000, right? 18,000 bees per year. Okay, and there we are. So we've shown it's approximately 18,000 there. Okay, again, important to recognise you multiply by 1,000 at the very end, because that's because the number of bees again is thousands, right, of NB. So we need to at the end account for that. Okay, so I'm going to get rid of some of this now, but part C is where it really kicks in. So now we're told the number wasp in thousands again, right, is modelled by the equation NW is equal to 10 at 800 e to the negative 0.05t. Yes. Then when t is capital T, according to the models, there's an equal number of bees and wasps. So when there's an equal number of bees and wasps, well, that means that therefore the two NB has to equal NW, right? Which means the two equations have to be equal. So that means NB equals NW. Well, therefore, NB, the equation for NB here of 45, add 220 e to the 0.05t, that has to equal NW. So NW is 10 here, 10 add 800. negative 0.5t. So hopefully you're with me there. When there's an equal number of bees and wasps, which are what these two formulas are telling me, they have to be equal. So I'll just set the two equations equal. So at that point, then it's asking me to find the value of t, effectively. That's the hard part, right? I need to now solve this equation for t. But we can't take logs at this point. If you try it, yeah, you'll be in for a very rough time. You won't really get anywhere. What we need to do, firstly, we're going to rearrange a bit. Firstly, I'm going to move, again, like we've been solving equations normally, just move all the t's to one side, so I can sort of rearrange. So 220e to the 0.05t, then t, subtract 800 e to the minus 0.05t, then I'm going to get 10 take away 45, that's going to be minus 35. Now actually what I'm going to do then is add 35 to both sides, equal to 0. Now hopefully, it looks awful, but hopefully this sort of equation is quite familiar. We did an equation like this earlier, right, in the video. If I'd cast your mind back to when we looked at, where was it? This equation here, it's the same sort of thing. I've got e to the positive x and e to the negative x. I've got here, instead of x, I got e to the 0.05t and negative 0.05t. What I can do here is then, I've got a hidden quadratic, right? It's the same sort of equation I did earlier that I've just shown. To spot this, I can convert this negative exponent as a reciprocal, right? If I use my power law, a negative power means it's a fraction. So I can say that this is 220 e to the 0.05t minus 800 over e to the 0.05t. Add 35 equal to 0. Then I can times by e to the 0.05t. So what I've got is 220 e to the 0.05t squared, right? Because I'm multiplying by itself, right? E to the 0.05t times again by itself, it's squared, right? And then minus 800, add 35, e to the 0.05t equals 0, right? And then if I just rearrange ever so slightly, I get 220 of e to the 0.05t squared, add 35 e to the 0.05t minus 800 equals 0. And now hopefully spot I've got a hidden quadratic at this point. If I say u is equal to e to the 0.05t, therefore 220u squared add 35u minus 800 equals 0. Does that simplify? No, it doesn't. Not nicely anyway. I can't cancel down the coefficients. That doesn't matter. I can just use the formula. So then u is minus 35 plus or minus the root of 35 squared. Take away 4 lots of 220 of minus 800 over 2 lots of 220. And so u, if I solve that, I get u is 1.829 roughly to 3 dp. That's what it gives me. I don't get a fraction or anything like that. Or u is minus 1.988, again to 3 decimal places. And of course I want to solve for t, not u, so that means e to the 0.05t is equal to 1.829, or e to the 0.05t is minus 1.988. Well, this equation, firstly, I can just take logs at that point. So then, ln e to the 0.05t is ln 1.829. So then I can bring the coefficient to the front of the log, to then get that 0.05t ln e is ln 1.829, but of course ln e is just 1, so simply 0.05t is equal to ln 1.829. Therefore t, if I simply divide by 0.05, t is ln 1.829 over 0.05, and that will get me t to be 12.08 to 2 decimal places. Then I need to solve this one, but actually I can't solve it because spot this, again I got an exponential equal to a negative, that cannot happen, okay? E to the 0.05t always has to be positive above 0, therefore cannot be negative, hence no solutions there. Okay, and again, if you were to take logs, you'd spot very quickly you're going to take the log of a negative, which can't happen either. So there's no solutions here. So the only solution is indeed 12.08. So there we are. That's it. Okay. The value of t. So that's big T. Okay. Big T is 2 decimal places. Well, yeah, that's 2 decimal places, right? So we can just say that big T is this. And there's my answer. Okay, that was horrendous. That's probably one of the worst hidden quadratics equations to solve in in A-level maths. One of the hardest I think I've ever seen. Probably one of the hardest disguised quadratics at least, but yeah, okay, that was quite gnarly towards the end, but hopefully that made some sort of sense. But yeah, so now hopefully you're quite comfortable with logs, how we can essentially solve equations using logs, and how we can use ln, right? This ln is quite useful, right? It's a lot quicker and easier to use once you get used to it. But yeah, and hopefully you're confident with exponential modelling as well. These are very common exam questions, so hopefully, again, you're quite confident with it now. We've looked at a good few modelling questions now. But yeah, so next time, we're going to look at log modelling. So we looked at exponential modelling, now we're going to look at log modelling, logarithmic modelling, more modelling. But yeah, so that's it for now. I'll see you next time.